Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so we're very, very happy to have Bill Freeman here from next door. He is one of the top people in vision, and he is also the thesis advisor of one of our new postdocs, So he's going to be talking to us about where computer vision needs help from computer science and machine learning as opposed to computer science.
Well, so thanks a lot. It's a real pleasure to be here. I've heard about this lab, and it's very nice to join and engage with you all. And also, I'm glad to take part in this communal experience, which I'm told is what the lecture is like. So that's fine. Yes. So here's what I want to talk about. Just a little bit about my background so you can get used to hearing my voice, and then computer vision applications, and then techniques and problems that we need help on. So first about me, I've been around for a long time, I guess. So I worked originally for 6 years at this company that's now bankrupt and gone, Polaroid, as an electrical engineer working on electronic cameras and printers. So there is an Apple II that we programmed on and made a so-called video printer that would do this amazing thing. It would give you color prints from your computer. Sorry? What year? 81 to 86. Yeah, we had some pads on it, yeah. So the printer was a black and white monitor that exposed color film through 3 different color filter wheels. And we thought that was the coolest thing. Okay, so then my wife and I wanted to have an experience living in a foreign culture before we started having kids. So we lived in China for a year, and I was a foreign expert. Through no intention of our own, we picked really the world's most polluted city. I think it is the most polluted city in the world. Taiyuan, Shanxi, China. And so there's us driving on the family transportation around campus. Sorry?
Who do they serve in the foreigners' cafeteria?
Well, they serve really good Chinese food. And then typically, so I lost 20 or 30 pounds. And typically men lost weight and women gained weight. I don't know why, but...
You're pedaling the bicycle.
Sorry? Yeah, right. So when I was in China, I read this book, Vision by David Marr, and I got really excited about computer vision and vision. And it's going to be reissued this year by MIT Press, so if you want to also get inspired by it, I really recommend it, even though it's 20 or 30 years old. It's just a beautiful book. So I applied to MIT for grad school and came there. And then after 4 years, I worked at, get this, a fundamental research lab that was across the street from MIT for 9 years.
And what happened to it?
It's still there. It's
the building.
No, it's still going strong. And I was the only vision person there when I was hired, so I feel a real sense of camaraderie with Suh, who's in a very similar situation. But here's what happened. A lot more vision people came, and then we got a big vision group after that. Anyway, so here's me. So it was a really wonderful lab. It's not quite as fundamental now as it used to be, but we could do what we wanted to do. And then actually this is a picture of my more applied projects. It's a television set that you could control with hand signals. So there's the user there, and you hold up your hand and the TV turns on and has some on-screen controls, and then you move your hand and the computer would track your hand and let you use it like a buttonless mouse, and you could adjust the controls that way.
This is all vision.
Right, all vision, yeah. And then in 2001, I moved to MIT, and I've been faculty there since. So I have a sample of 2. Everyone I've talked with at this lab tells me they're free to do what they want to do. And also I know that each of those, my sample of 2, are really smart people. So I thought, wow. So there's a whole audience full of really smart people who can do whatever they want to do. Why don't I get them interested in my problems? So that's the goal of this talk, actually. So the audience are 2 people. One is anyone who might want to dabble in vision. This talk is for you. And then the other for people who don't think they'll dabble in vision but want to just learn what's going on in vision. This talk is also for you.
And for the game theorists in the audience, they have to figure out why you wanted to make this incentive compatible.
Incentive compatible?
Why you're telling the truth. Why you're telling the truth instead of trying to trick us.
Oh, I see. Yeah. Because I'm not that smart. I think I don't know. Okay, so the way I want to structure it then is kind of start out by just talking about existing computer vision applications, what's out there now, and then talk about sort of where we're stuck, and this is a kind of a mix of where we're stuck and interesting problems to me. So things in low-level vision, things in high-level vision, and then miscellaneous problems. Okay, so here's, just as a way to start, here's a list of companies that are involved in computer vision. Let's start with the first one, Cognex. Cognex is kind of an old-style computer vision company. They do computer vision for manufacturing. So there you're going to have controlled lighting. It's going to be like a factory. You can control everything, really, and you have the task of doing computer vision. So it's almost a different animal as far as the problems go because you don't have all these issues of lighting variations, size variations, occlusion, all the uncertainties that you have in sort of real-world vision. But they're a successful company. They're in Needham, I guess. Yeah, and they've been around for a long time. There was, what can computer vision do? Well, it can save lives. So here's a company that installs cameras in swimming pools and looks for people who've drowned. Or who are about to drown, sorry. Who have not yet drowned. So, but it's successful at finding people who have not yet drowned. And they have them installed in all sorts of places in the US and Europe. And, here's from the London Times, saved by a computer lifeguard. Someone's at the bottom. And the lifeguard, for some reason, it was such a crowded pool, they actually couldn't see the person at the bottom. But the camera system could see them and alerted the lifeguards. So this is, this is a great application for computer vision. What makes it easy, I guess, is the fact that you've got the stationary camera and the pool doesn't change. Lighting variations are going to happen a lot, and so you have to learn to recognize someone still on the bottom, but they can do that.
So if I dive and hold still for a while?
That might, yeah. I don't really know the limits of this thing, but I would assume that if you dove, hold still for a while, held your breath, that something would go off, yeah.
And if you stay there long enough, you will drown.
Yeah, right. Yes. So here's another application, which is always about to happen, but I really do believe it's about to happen. This is an Israeli company founded by Amnon Shashua, who's a former MIT graduate student, who is, without a doubt, the richest computer vision researcher in the world. I think he's like worth $500 million or something, based on this company. And they are going to save a lot of lives, too. Initially, though, they'll just help people drive. So it's a single camera system. It is installed behind the rearview mirror and looks ahead. It gives you, there are other things it can do. It can give you lane warnings if you drift across a lane. It can adjust your brights to account for an oncoming car. And over time, these things are going to take more and more control over your driving. Initially, it's just going to be a whole lot of warnings.
Are they in use?
Right. So that's the thing. Every time I talk with them, they're going to be installed in about a year Mercedes-Benz. Yeah, so they got, billion. Yeah, they had, I forget which company it was who bought like a third of them. No, they acquired actually a third or a half of them. Anyway, he's doing well. And also, this company's doing well. So that's actually really exciting. I thought that how could they possibly compete with, GM and Chrysler and stuff? But actually they're they've got 25 people working for years on this one problem, and they're going to nail it. They've got a real-time system that does this better than any of the companies' labs do it. Okay.
You have no idea what it's like.
Okay. But so they're doing it right. Yes.
What's the advantage of using vision for this as opposed to requiring that all new manufactured cars have some kind of radio transmitting chip installed?
That only takes 20 years to get finished.
Yeah.
Yeah, so there's a transition period, but like.
Yeah, we need to work in China.
Well.
That's a 20-year process anyway of every year.
Yeah. Well, so I guess the answer is I don't know all the trade-offs involved. I know one thing is that the industry is extremely cost conscious, and the big thing that helped this company start was the fact that instead of using 2 cameras, they were going to use 1 camera, and that was their big advantage because they didn't have to have 2 cameras and they didn't have to have these calibrated cameras. And if you could do it all with 1 camera, then everything's so much cheaper and simpler. So they're sensitive to that kind of a price difference, 2 cameras versus 1. So I don't know the direct answer to your question of what about other particular ways of doing it, but this has the advantage of just being able to do it 1 car at a time. Let's see. Okay, then at Merle, the lab in Cambridge, I worked on computer vision for computer games, and these have actually not the ones that I worked on, but others have come to market. So this is from the Sony iToy, and of course, Microsoft will have its own version coming out. Not directly based on, not only based on vision plus depth also, is my understanding. There's a lot of interest in computer vision for identity recognition.
We have some people here working on this.
Oh, really? Okay. And then there's, do I dare say this word here? There's Google, which of course uses vision for to help you with finding the images that you want. And there's Microsoft, which has a wonderful photosynth system, which, from talking with my friends in the research, they have all these ways in mind that it can start making money. And then these are not current camera companies, but they're just things that obviously have to happen. Surely household robots will have vision in the future, and surely that's going to happen and be a big application. And then another one is surely vision will be used to analyze YouTube content to optimize ad placement. And I just know a number of companies that are working on that particular problem now, and surely that will happen too. So these are other future applications for computer vision. Okay, so that's kind of a little survey of where it might be useful or where it is useful. And then now I want to talk about specific technology. And I got to say, this is not a talk about a particular research project. It's a talk about a research field. So the way this is structured is to kind of give high-level things about particular things I've worked on or am familiar with. So feel free to ask questions if you want to go deeper. Okay, so you can kind of divide the vision world into low-level vision and high-level vision. High-level vision is recognizing objects. Low-level vision is like sort of image in, a field of numbers out. So you might want to know what does this image look like if it were made sharper? What does this image look like if it's were deblurred? Other things like that. Whereas high-level is kind of image in, string of characters out. High-level interpretation.
Almost a single image, not a camera with depth perception.
Let's see. In what I'm going to be talking about, it's almost always a single image, but that's certainly not the field. That's just kind of my bias. Stereo is an important part. Video is an important part.
Just correcting for the lighting on low level and high level.
I would call it low level, and sometimes you need to do low level in order to do high level successfully. Yeah. Well, because it fits in this taxonomy. If the output is a field of numbers, then I'm calling it low level. But you might need to have high level interpretation of the image in order to do it right, I suppose.
That's what I was wondering.
Yeah. Okay. So, all right. Well, let's start with fundamentals. All right. How do you take a picture? Well, in the old days, you got lens, you got film behind it, and took a photo. Nowadays, the image is just a set of data. It's not the final output. And this opens up a whole new sort of technological area called computational photography. So it's no longer lens to film, and then here's the image. It's really lens collection to sensor, and then you have to interpret your sensor data. So there's been an explosion of cameras because of this degree of freedom now. We don't have to stop at the image anymore. So you have trinocular, binocular cameras. You have coded aperture cameras, which I'll talk about a little more in detail. Multi-lens cameras that give you a picture of every light ray coming in every direction. And this one is very cute. I don't have time to explain too much in detail, but it's called wavefront coding. You make a blurry image, but you can decode it and make everything be sharp. So it was a real nice advance from about 10 or 15 years ago.
Any blurring?
No, it's blurred in a particular way so that all images at all different depths are blurred in the same way. So if you just looked at a photo that you made with this crazy lens, it would be blurry. But it has the benefit that if you then process it with a computer, you can make every depth be in focus. You can have sort of an infinite depth of field.
So you can choose to make any particular depth.
Actually, with this one, you can only make all the depths in focus. With this one, you can make any particular depth in focus. But the idea is the same, that you're going to make some image that you then have to post-process by computer to pull out some feature that you want from the world.
But it's not secure in the sense it's not a way how I could make you buy my art by sending you a blurry image and only if I send you the key you can make it.
Right, it's not secure, exactly. And actually, I'm going to talk about trying to do that in a bit also. So we just want to sort of frame this problem in a mathematical way. So what does a camera sensor element record? Well, here's a scene, and I always try to put pictures of my children in the talks. So these are my 3 kids. They're on the fence. Light comes out in all directions here and goes through the camera optics in some crazy way and lands at, say, a particular sensor element. So first of all, here's a pop quiz for you all. What is the dimensionality of the set of all rays coming out in the world? Is it a 2-dimensional thing, a 3-dimensional thing, 4-dimensional, 5-dimensional? Well, so here's how I think of it. From every position, you've got a 2D sweep of possible positions that the ray can be coming from. And then at any given position, it's got 2 degrees of freedom it can go in. So the set of the so-called light field, the set of all possible rays emanating in this room, is a 4-dimensional thing.
Wait, why only 2 directions?
2 degrees of freedom. So you've got the
2 degrees of freedom. Okay.
Yeah, 2 dimensions. Yeah. So mathematically then, the light field is this 4D thing that we're going to rasterize as a single vector. And then what does the sensor see? Well, it sees some projection, some positive linear combination of the elements of this vector, and then you add a little bit of noise, and that's what 1 pixel sees. And then here's a camera. The camera is some matrix T that does some linear combination, different potentially at each different pixel, of all the light rays coming in the world. And then what is photography? Photography is solving this equation. Okay, here's your sensor data Y, and you want to, given T and knowing about your camera and having your sensor data, you want to figure out what X was, which is the set of all.
Bound on the norm of n, or not?
You could phrase it that way. You might have some estimate of the variance.
This one you only have 1 imager?
Yeah, I mean this matrix
T. Story about the image is not enough.
Well, this matrix T could describe a stereo camera. Yeah. Well, it'll work. So you could have this. The set of all light rays in this room is this 4D vector, and camera A over here takes 1 linear projection of it and gives you that top part of your observation matrix, and then the bottom part of your observation vector is formed by taking some other linear combination of the. Well, there you go. This is really underdetermined. Maybe that's what you're getting at. I mean, so this is a little, in general, a 2D projection, and this is like this 4D animal, how can you possibly estimate it? Well, there you go. This is the main point of part A of the talk. You need good statistical priors on images and on light fields, because otherwise you can't possibly estimate it. Linear. Wait, you mean this? T. Well, I guess because I'm sweeping all the nonlinearities under the rug. I'm assuming you can sort of back them out. I mean, CCD sensors are pretty well linear. And then if you have a regular camera, it goes through this distorting nonlinearity in order to pre-distort it in anticipation of being shown on a monitor. But in general, you can often, in so-called camera raw format, get out something that's pretty close to a linear function of the light.
But it's not, I mean, you're talking about the space of the ray, which is sort of the angle, and my lens will not necessarily, the output angle may not be linear and the input angle because they make frequency interactions.
Right, so all that stuff is encompassed in this matrix T, which, so this thing X is each little element in X is one ray at some particular angle, and then this matrix T tells you how much of that light is going to land on any given sensor element. So the nonlinearity of this thing bending over to there is all described in the positions of this. Okay, color. So then you have a different matrix.
Maybe sort of broken different. I mean, red gets red
Yeah.
differently from blue. And
Right. So that you can also talk about that in matrix T. So you can break up Y into maybe the red parts are up here, the green parts are there, and the blue parts are there. And then this matrix T is going to be different for each one of those colors. You could describe it that way.
Okay, so T will depend. So you have different T's.
Yeah. So one camera's going to have one T, another camera's going to have another T, and as a camera designer, you're free to make up any physically realizable T that you want. So let's look at an example. Yeah. So this is what's nice about it. It turns photography into an inference problem, solving that little matrix equation. So let's look at one particular example of all this. Let's talk about lenses and defocus. So now we're kind of back in the conventional ordinary lens, and here's the focal plane, here's the camera sensor. If we move back from so this is a conventional lens. If we move back from this plane of focus, it focuses there, and then at the sensor you get a blurred image, and if you move back more, you get a more blurred image. So you have a depth-dependent point spread function, and you can sort of use. I mean, when you look at a conventional photo and you see really blurry things, you say, well, it's probably in the background. You see something really shy. Well, it's maybe in the foreground. So you can a little bit use it to estimate depth, but there are a number of reasons why it's difficult. You can make it a whole lot easier for yourself if you say, aha, I'm not going to use a conventional aperture. I'm going to use this aperture. Okay, that's my camera aperture. Now, you've got this specially designed code, and now when you change depth, so here's actually a picture of the image at the sensor of a point of light at different depths, and here's sort of the schematic of how it looks. Now you have this, again, sort of scaling according to depth of the object, but you've now sort of introduced this modulation into the point spread function, and you've designed it in a clever way so that it's easier to discriminate different depths. So what's going to happen? This is the so-called point spread function. How that relates to the image you see is the image that's in the world gets convolved. Everyone with me still? Want to say convolved? Okay, it gets convolved by this point spread function. So you want to design this thing so that if you take an image, convolve it with that, you can now easily distinguish what parts of the resulting image are blurred by what size of this thing. So now the resulting image is a kind of a folding together of the actual image plus this funky little point spread function that you've designed. And you want to design it in a way.
You only have one particular point spread function.
Well, so each different depth, right, only one. So it's spatially, it scales with the depth of the object. So you've got the scene there. Each different depth is going to give you a different size of this point spread function, and it convolves with the image. So now you get another image, and you have to decide So is that what it really looked like and it's just a sharp picture of it? Or is that thing blurred by this funky thing at some depth? So you have to make that decision. And so if you have a conventional aperture, it's going to be different scalings of this sort of pillbox function. And if you have this coded aperture, it's going to be different scalings of this funky thing that we designed to be very easily discriminable. If you're an electrical engineering crowd, this has nice zeros in the Fourier transform, and as the thing scales, you can identify what the scaling is by what frequencies in the resulting convolved image are zeroed out. And so that you can design this thing to make it easy to discriminate what depth it's been blurred by.
Is part of the reason that's useful because you don't see that much in the real world? Is there a particular pattern or anything?
Yeah, that's part of why it's useful. It's like the odds that you'd come across this thing in the world are
Much lower
very
than
small.
the chance of little dust.
Yeah, yeah. And then here's a little kind of just visually intuitive thing to explain this. So all of these images have been, yes, I guess so they've all been blurred by this size of either this one or this one, and then you try to unblur them by the wrong sizes or the correct size. If you have this conventional aperture, you can then this image convolved with this explains what you see, or this image convolved with this explains what you see. Either one explains the data pretty well. So you can either say it was blurred by a big blurring thing and it's kind of sharpish, or it was blurred by just a little tiny blur and the thing itself out there was really quite blurred. So you have this sort of metamer, this two different ways of explaining your data, whereas with this engineered aperture, it's much clearer that this is the only solution that explains things. So
in a sense, you're able to perceive the depth from the image.
yeah, so it's like a 2-for-1. You get out both a full resolution image and an estimate of what the depth is, because you can deconvolve it. So here's an application, digital refocusing from a single image.
Turn off the lights by the way.
Yeah, is that like just for these slides? Is that possible? I mean, the video projectionist will come in and kill me, but but just for these slides. Okay, so let's see. So here's an all-focus image we've recovered. We've estimated what the depth is, now that you know the depth, you can go back and say, well, I'm just going to, I took the photo, but what I really wanted to do, I really wanted to focus on her and have the other people be blurred. So now that you know the depth everywhere, you can generate that image. So this is refocusing after the exposure. And then now you say, oh, no, I didn't want to get her. I really wanted to get him. But again, you've just from that same picture that you took that has sort of the image and the depth information all folded together in one data set, you can deconvolve and get this guy sharp and the other two blurred, or you can do the last one, get him blurred and the other.
You're putting in some kind of prior for the image.
Right. In this case, that's great. What was the prior? So it was it was high kurtosis. The gradients had a particular distribution that they really wanted to be zero. In other words, every pixel really liked to be the same value as its neighbor, but occasionally it could vary, and it could vary in a particular way. And that's actually that story is the whole point of this first low-level vision part.
These are kids.
Sorry? No, those are not my kids. They're students. A sort of kid. Yes. So here's my first. So what I have in whatever fraction of my talk I'm going to get through, here's the common format for some of these. What the problem is, applications of it, and references in case you want to pursue it further. So here the problem is, how do we design this camera transfer matrix to optimally record image information and also allow optimal reconstruction of depth? There's actually this trade-off in designing that little code. You can make it really easy to discriminate depths, but then you lose something. It's harder to actually find out what the data was at those depths because you have to throw in these zeros in the Fourier transform, and then you've lost that information. So there's this tension between identifying what the depth is and recording all the image information at all the depths. So that's a problem we don't know how to solve. If you're interested,
In
Yeah.
the general thing that you had, y equal to xt plus
Yeah.
theta or whatever,
Yeah.
is it interesting enough to just ignore noise for a while and think about the rest of the problem? Is that
Well, I guess yes if it works. I mean, the noise level is pretty low, and the signal-to-noise ratios are really pretty high. So as long as you don't do something that's really unstable, it will probably work to ignore noise.
how to design this thing, but there's the question of what did I know about the image? Like Butler was asking what's the prior,
Right.
right? So, and that's what varies your different. That's the reason why you pick different keys.
You mean different priors? Well, that's we have just kind of. I'm just going to show you an example in a sec. There's only one really good prior that people have, and that's a real shortcoming in the field. And what we really need are better priors. T's got all these other constraints on it. You've got to decide what you can actually build, and so that's
It's not a prior over T, right? It's a prior
over X.
Set of solutions to X. You think about T being fixed. And then
Yeah, yeah, right.
Is there any connection between this and compressive sensing?
Yeah. So that's it's yeah. Why is that a painful subject for me? So we've looked into compressive sensing, and we kind of think it's not all that useful for images, but it does have a yeah. It's a related problem.
Because it's a completely different kind of prior technology to make.
what's your next slide?
I'll answer your question. Yeah. Well, we'll talk more about priors. So, okay. So that's actually this is the main point of this low-level part. The real shortcoming in vision and image processing is that we don't have. We're just a long way from having a great prior on images, and it's a really interesting field, but we're just not there. So if you had a wonderful prior on images, in other words, you could draw from your prior, get something that looked like an image. You can take a noisy image and combine it with your prior and get a great-looking image out. That would just be so useful. Every low-level problem you can imagine needs a strong prior on images. Here's another example, another problem: noise removal. There's the original. You add a ton of noise. Now you've got this in the sort of, everyone knows Bayes' rule, I assume. Oh, anyway, you've got this tension between the so-called likelihood term and the prior term. And then you've got this lambda that you dial which one you favor most. If you say the likelihood term, if you really, really trust your data, then you say, okay, that's my estimate of the image. You know, there it is. I trust the data. But if you say, wow, that's such an unlikely looking image, I think there's a lot of noise added to it, and I'm going to estimate what the underlying image was and estimate the noise. And so there's this knob where you adjust how much you trust your image, how much you trust your prior, and there's like here's one compromise between the two, and it just doesn't look like very image-like at all. If we had a great image prior, when you cranked up the thing saying, I really trust my prior on images, you'd get something that looked like a good image. But nobody gets things that look like good images now. If they really crank up their prior, they get stuff like this. So there's a place where we really need good priors on images. And what is a good prior on image? Something that you looked at, you say, okay, there's a good image. And if you cranked up your prior knob, you would get something that looked like an image. It wouldn't be the right image, but it would be something that looked like an image. And so
The fact that this distinction between low level and high level isn't going to work.
it could be that. I hold out hope that you can go pretty far even without high-level stuff. But
So what kind of prior can you imagine?
well, for example, a non-parametric prior. If you went and had a billion patches of real images, and you went and found the closest one to each one of these, I think you would do a really good job at removing noise. Yeah.
People do that for simulating high resolution, like hallucinate
Yeah.
extra pixels.
Right.
But you say it's much harder to.
Well, no, I mean, I think it's a very similar problem, and I think people have made a lot of progress with doing that.
Better than these pictures.
Yeah, these are done sort of parametric priors. Okay, here's another problem that requires good priors. That's removing blur from cameras. So here's a picture that tells the whole story. This one's got the subject and the photographer in the same picture. She took a picture of herself with a mirror, moved the camera during exposure, and that's the output. And so here's the result of our algorithm, which uses this prior that I'll explain in just a sec, which tries to look at this and say, okay, even though I've got only a low-level understanding of the world, I'm going to try to guess what the image was, and here's the best guess. And here's a close-up of it. Whoops. Original, and this is just to show you that it's a hard problem. Here's just boosting the high frequencies, sort of naive sharpening. And then here's, yeah, yes. Yeah. Well, there's what you should do and what we do. What you should do is what Kodak does sometimes, and they get a lot of people in a room and say, okay, here's image A, image B, which one do you like better? Okay, here's an image A, image B, which one do you like better? You know, and so forth. Supervised learning. Yeah. Or just have people tell you what looks best. It's a whole.
Taking a really good picture of what comparing it with.
It's more like a measurement.
Yeah. Well, taking an unblurred picture and comparing it is a good thing, but in some sense, you'd think that's the gold standard. It turns out, however, that like looking at the sum of squared difference between the pixel values is not always a good indicator of how different it seems perceptually to you. And so that's actually another little subfield that nobody's really solved well. And how do you get a nice mathematical measure of the visual dissimilarity between two pictures? And that's a field of open research.
So it's that you don't have good metrics.
Yeah, I mean, doing the obvious thing of taking the sum of squared differences between the two pixel values is subject to some really, for example, the trivial thing, if you had like a 1 intensity level difference between them, but you lined it up so it's in vertical streaks, you could see that right away. Whereas if you randomized it, you couldn't see it at all. And that's just one of many different things that messes up the so-called squared error criterion. And I should say just right now that,
I believe that the square error is.
yeah,
But there are much more specific metrics.
you would think. There's some. So I got to tell you right now, the person I think who's really the best for almost every low-level vision thing is my former MIT office mate, Eero Simoncelli. So he's a professor at NYU now, and he's just great. He's come up with this, what I think is the best so far, perceptual error metric between two images. And anyway, so his webpage would, if you Google EERO, which is his first name, you can get him, at least on the first or second listing. And anyway, he's really good at these sort of metrics. So, okay, let me just kind of frame this problem. Here's your data, blurry image. And here's what you want to find. You want to find this explanation for it, of a sharp image convolved with some unknown so-called blur kernel. Okay, I just want to explain what this is. This is a picture of what you would see if you photographed a little speck of light and moved the camera in the same way that you did when you made this picture. It's the so-called impulse response. It's what a point of light would give you. And then the thing is that every point of light gives you that, so therefore that instructs you to convolve this thing with that latent image, and you get your data. So that's your model for your data. And what I love about this problem is it's just beautifully underdetermined. So here's your data. Well, how can you explain the data? Here's one perfectly good way of explaining the data. That's what was out there. And you took a sharp picture of it. You know? Particularly from this low-level point of view, you have, why isn't that it? Is that something wrong with that pile of numbers in some way? Well, that's where your prior on images comes in. Here's another perfectly good explanation of it. That was what was out there, and you moved your camera such that the point spread function looked like this. And that would also give you that data. Okay? And then finally, here's another one. Could be that was there, and you move the camera like this, and you give that. All these perfectly explain the data. How do you pick between them? Well, you've got to have a prior on images. And you can have kind of a high-low prior or low-low prior. A high-low prior, you have to go and say, okay, this is buildings. I know the building edges are supposed to be sharp, so it can't be right. But that's just going to be hard to do. You can't, certainly at this stage, I don't think you can do a high-level interpretation of every image.
Yeah.
What you really want is a nice low-level, signal-level prior that will let you look at these things and say, I think this is the right one. You know?
Do you also use priors on the blur?
Yes, you can also do that. So I should say in this work that we're doing, we have a sort of pathetically weak prior on blur kernel. It's just it's got to be all positive and it's got to be sparse. But you could have a sort of stronger one saying that there's got to be some kind of low acceleration trajectory of the camera that explains the whole thing.
But you're not doing that.
No, not now. But you all are great at this. Here, just try this out. Sharp or blurred? Blurred. You've never seen this picture before, but you can figure out there's blurred. This one? What do you think? I think sharp, yeah. And that one? Blurred, yeah. Okay. So you're very good at it. So here is our prior, which sort of does okay. It's sort of, I mean, and on the one hand, this is what we've done. On the other hand, it's really a long way from what you need to do. A number of people have pointed out that if you look at the statistics of a gradient operator or really any bandpass filter operator on images, it looks very different than it would look like on random noise. It's so-called heavy-tailed, crototic. So here's the value of the gradient. This is just the difference between consecutive pixels. And here's the histogram, the log frequency of occurrence of how often those difference values occurs. So most of the time, an image pixel is the same as its neighbor, and then every once in a while it changes. Yeah?
Gradient, I don't know what it is. Is it reasonable to think of it as some linear function applied to the image?
Yeah, it's the operator 0.5 minus 0.5 convolved with the image. That's what I mean by this.
You say that it's heavy tails, but presumably there are different heavy tails for different kinds of pictures. Or
Yeah, a little bit.
but not as much as I might guess.
Yeah, right. You've got it. So, and if you take a blurred image, it's going to have a different histogram. And so this.
Is there like some power law that characterizes?
Yeah, there's a little. Yeah, I mean, it does depend somewhat on the image. So what we did for this work was we fit a function to this curve, actually for this image. This is our model for all images, this image right here. And we fit a little parametric model to that histogram and said that's what we think that's our prior model on the gradients of images. And now that's weak in so many ways, but it kind of works.
Try taking a million sharp pictures and doing machine learning on them.
What does it mean to do?
This out.
You mean to?
That's some space possible.
Yeah.
And you do some machine learning thing.
Yeah. Yeah. I mean, actually, your colleagues at Microsoft, at Redmond, my summer intern just came back and told me what he did, and actually that was his summer project, to go come up with different. They came up with a 2-parameter model for this thing and come up with different parameter settings based on different parts of the image. So you can do better than what we're doing, but this is what we did, and so then here's the problem now. We've got the reconstruction constraint that whatever you estimate for the image and whatever you estimate for the blur has got to convolve to what you saw. We've got this prior on the image gradients, which is going to help you identify what this should be, and we've got this weak prior on the blur kernel, and then we did the sort of Bayesian estimation, try to solve this. There's some details. It turns out you don't want to actually try to estimate both the blur and the latent image at the same time. What you really want to do is estimate the blur kernel and marginalize over all possible latent images, and then fix that and estimate the image. But that's another talk. And so this is Bayes' rule. This is your likelihood term, and here's our little prior saying that we want the gradient values to have a certain distribution, and then our prior on that.
This is a nice little
Yeah,
curve that
yeah,
you fit to.
yeah. And if we could just do the lights one more time, please. I don't know who made it happen. Oh, wow. Incredible. Okay, so here's the output of it. The original photograph inside a museum. You're not allowed to take flash. And here's our estimate of blur kernel and our estimate of the image. Now, there's all sorts of problems which you could speak up, and this is where we need help. Anyway, there's it's still kind of noisy, but it does a good job in general. Yeah, but that was, I think.
In the image or
Yeah, I mean, well, no, I think we could have done a better job at matching the colors. I think it's just a kind of a global 3x3 matrix we could have estimated at the end. I don't know why it's not better than it is. Here's MATLAB's econ blind. Nothing against MATLAB, but it's a hard problem and it doesn't do very well. So here is a close-up of the original, the sort of brand X reconstruction, and our reconstruction, which,
So
properly.
Comp blind is using what kind of?
It's using Richardson-Lucy deconvolution and doing it in an iterative way to estimate both the image and the blur at the same time. It's
The
a
difference between that and what you were showing us.
is they don't have an explicit prior on their image in that.
So the big assumption that both image and the blur kernel second order processes.
Okay.
It's not like sharp.
Okay. All right. So it's a kind of a more Gaussian-like prior. And just one more thing about priors and images. So another way to look at this problem is if someone gave you a stack of a billion patches, what's a good way to model it? And this is what people have come up with so far. This is this is an analysis based on looking at lots and lots of images. If you take a sparse linear combination of these, you can model these little 16 by 16 image patches very well. And this was a kind of a breakthrough paper in the year 2000. What's cute about this is it looks very similar to receptive field responses in monkeys and cats and things. So there's some sense that mammals in the early stages of visual processing are pulling out these little kind of fundamental little atoms of the visual world. And we can find them too if we process our patches properly. But this is only the first step.
Some basis.
Yeah.
For
Yeah, for images, for all patches. If you take a sparse, and that's the thing, it's not just a linear combination. You can do PCA and get that. This is a sparse linear combination. Take a sparse linear combination of these, you can reconstruct all their training image patches in some optimal way, optimizing the particular function they had.
So is there some, do you believe there's some theory out there, like wavelets, but not wavelets, where there's
Yeah.
some basis which would be some
Yeah,
sparse
yeah, yeah.
basis?
Yeah, so this is one good sparse basis. But then there's kind of more. There's the nonlinear stage, which is kind of yet to be determined on top of that. So these are a reasonable set of atoms you might try to build up image patches with. But we've got to go beyond just looking at those. I mean, so this is about 10 years ago, and I haven't really seen people go beyond it in a nice way. And so this is, I'm just kind of pointing out, this is problem number 2, statistical characterization of images, useful all over the place. Here's my office mate there. So here's some references that you might want to look at. This is the Deblurring paper that I showed you the results of, and we've done some other work on it, as have other people. So I want to get to other parts. I'm going to skip this Markov random fields. Just in general, for people who are Markov random field mavens, we need to handle higher order clique potentials, higher dimensional state variables, do inference on them better. That would be helpful to us. One last.
You know that
I know. I'm just trying to time this thing. I'm still about not quite halfway through the slides. So with the things I talked about before were kind of parametric style, low-level priors. I just want to show you what is, I think, the future, or what is just a wonderful present anyway. And these are sort of non-parametric priors for images. So there was this real breakthrough paper by a Berkeley graduate student about 10 years ago that just did, all these people done work on texture synthesis. And he came along and came up with the simplest possible texture synthesis algorithm, which gave results which were so much better than anybody else's results. And it's just the most brain-dead algorithm. Let me tell you what it is. Suppose you've got you've got this patch of here. Make me more stuff like this, and you're going to go on make. So like, there's your patch of reference stuff. Make me more stuff like this. Here's what you've built so far. You want to try to figure out what value should I put in that pixel. Well, you just go look at the neighborhood around it. Go find where you've seen that before. See what was there in those pixels, and take a random sample from them and put that there. And you go and do that, and you just get fantastic image synthesis results. You can also do it with patches instead of single pixels, synthesize a patch. And so here are examples. Here's the input stuff. The little small one is the input, and then the big one is the output. And you can just do, great texture synthesis. So you notice this is not the same image as that any one little place. It's another version of it. And you can do goopy stuff. You can do regular stuff. It's just a wonderful brain-dead way of making great texture synthesis. So here is sorry?
What happens if you take an image that's not just texture, they take a picture of a person and run this.
Right. So so you'll.
your children.
Yeah.
I mean, it seems like it should be interesting.
Yeah. So, it kind of does what you would expect after you think about it. So it depends how big your patch is that you're grabbing pieces of. If you've got a really big patch you're grabbing pieces of, one that covers the whole face, then you're going to come up with a face because you've got that, you're sort of enforcing that regular. But if it's really small, then you're just going to come up with little contours that are some horrible, distorted, creature. Yeah. 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 Sure.
So the cardboard between between the apples and the...
Yeah, right. So there's a bug right there. Yeah.
That's an artifact of the...
Yes. Yeah. It couldn't. And here. So actually, this is it's a little bit symptomatic of the algorithm used to make this. It's done in a raster scan way in this particular thing. So you sit there and you try to match. Here's the picture of it. You're trying to come up with this patch. So you say, well, I want this border to match this patch above. I want this border to match this patch there. And these are unconstrained. So you might imagine that you could sort of paint yourself into a corner in the bottom right. And actually, that is kind of what happens on that picture. It's a little more artifacty down here than it is up there. We have more freedom to choose things.
There are so many more wormholes.
I see. And there's only, sorry, this is on a
there's
timer.
only-
There's only one here, but there's lots of them there. Yeah, this is the one that has, you see all the way around in this one. Yeah. Yeah.
With the borders of the apples.
Yeah.
Other ones, those are the complete.
Yeah. So this is another, I don't know, another good kind of computer sciencey problem. How do you construct and manage a nice non-parametric signal prior? So how do you select the exemplar? So this is these things are kind of weak in that they only reproduce one different particular texture stuff. You'd really like to have a non-parametric prior that just could do the whole world, and that's going to take a lot more patches. And so you want to manage these patches. You want to pick the right ones. You want to be able to find them quickly. And so one thing that's going to come up again and again in the remainder of this talk is good nearest neighbor search in high dimensions. Now that's supposed to have been solved somehow, but it's still a problem. So really good nearest neighbor search in high dimension would be really useful in computer vision. So now let's go to high level things, if that's okay. So this is low level, and mainly it's an underdetermined problem, and really the big thing is finding a nice prior in images. In high-level vision, I think of it as mostly a combinatorial complexity problem. So suppose you want to recognize chairs. Well, here are some chairs. Okay, go generalize from those and figure out.
Imagine that people wouldn't do so well on this.
Yeah, this is a hard one. But so, I mean, this just is an extreme case of within-class variability. Each one of these is a chair. It's hard to come up with kind of an image-based model for what that chair is. So just to kind of, so this is the high-level problem of image in and then words out describing it, for example. So there are a number of issues. You can approach the problem with a generative or discriminative models. So a generative model might have this kind of parts, and there's a relationship between them, and you can draw from this and.
And how come so the springs are trying to tell you that the mouth tends to be this far away from the nose, and
you get a little bit of penalty if it's there.
Blah, blah, blah.
Yeah.
So,
Yeah, it's describing the penalty for
like
violating.
Moore's law type penalty.
Yeah, yeah. And then this graphic is trying to say, well, you just have a lot of data points. These are faces. These are not faces. Learn a classifier. And then you can decide something to face by just seeing within an image enough of the little face pieces to say, aha, there's a face there. Or you can require that they be in certain configuration. These are really the issues that are going to kill you. You've got to be invariant to viewpoint, to illumination condition, to occlusion, to scale, to deformations, to clutter. These are what make the problem hard. And you've got to choose whether to look at little crazy features or look at pixels. I'll talk about that in a bit. So I sort of promised in the abstract a little history. It's not a big history. Just here I just want to show you what's happened in the past. If we go back in time, this is what people look like back in time. So little geometrical things. That's what computer vision researchers very reasonably simplify the problem and say we're not going to solve all problems. We're just going to say that things are geometrical and that's what we're looking for. And so we're going to try to find things like these. So here's the model we're looking for. Here's the input image, and aha, we found them. And that's the problem. And then it really becomes a kind of computer science problem where you have a interpretation tree, and you see how far down the tree you have to search. So this is some people, researchers at MIT at the time, I think, analyzed this. And okay, here's a real-world image, but now you've pre-processed it to just look at edges. And now you've got to go look at these little edges, these little edge features, and build them back together into your model and see which position and orientation of your airplane model best explains all this edge data. And so you can do that, and here's some more kind of geometric things. And so this is where the field was for a long time. And then, okay, but now back to the present. Okay, so now we're going to deal with real world images. Again, my kids, actually this is my son, that's my daughter, and these are their friends. So here, let me talk about the things that work. And well, this one, maybe I should skip that. But I just want to mention, I can't come to Microsoft and not mention it. One of the biggest advances in computer vision was made by Paul Viola, who's now at Microsoft doing search. And he wrote this paper, which I think is in pretty much every camera now. I mean, I haven't heard from how the camera companies are doing their face recognition, but this is like the only algorithm that could be fast enough to do it. So Paul came along and applied a nice machine learning problem, so-called boosting, which sort of takes the output of so-called weak learners, classifiers that are just a little bit above chance, and puts them together. And so coming up with a classifier which is really lousy but just barely works above chance, yeah, we can do that. You know, we can make plenty of those. For example, to find a face, you say, well, I'm just going to look for a feature that's light here, dark there, light there, and that's just does a little better than chance at finding where this face is. And so the boosting algorithm, is it all a standard lingo for you?
Probably not for him.
Okay. So it's a really powerful machine learning algorithm that it sort of corresponds to gradient descent in a particular cost function, and it sort of instructs you how to combine these weak classifiers to build a so-called strong classifier. And so you can take, in the sort of image version of it, you take many different filters and see how well they do at predicting whether or not there's a face there, and take the ones that do a little better than chance and combine them into a good classifier. So a number of the cute ideas that Paul had in his paper was to use these kind of ugly-looking filters, but use lots of them, and to calculate them very quickly using a so-called integral image where you don't have to, where you just sum every pixel value left to right and bottom to top in the image once, and then you can calculate all these filter responses very easily. And he also combined it with a cascade method. It's just a paper of about 5 elegant ideas, which was really the most influential computer vision paper in the past 10 or 20 years.
So what they're doing finally is, so the camera, when I click it, it draws these boxes around faces.
Yeah, I mean, many cameras, not all cameras, but many cameras have face detectors in them, and surely this is the algorithm they're using. I just don't know of any other they could be using. So that's a kind of a successful example of computer vision stuff applied, machine learning stuff applied to computer vision. Now here's a way that is really an open problem for computer scientists, and that's this bag of words representation. So the second most, or maybe the most, I don't know, tied for the most influential paper was this one by David Lowe on so-called SIF features. So here's the story. Originally, there were these so-called edge detectors, which look for little sharp edges in the image. But it's hard to build up you have to take a lot of edges to really build up an informative feature. And so, but on the other hand, you can't hardwire a whole lot of edge positions because any slight change in position or orientation is going to change it from your template. So you want to have a kind of rich descriptor, but at the same time that allows a certain amount of slop. So here's what David Lowe designed, and that's basically a histogram of image gradients. So this is a patch of the image, and here are the little gradient values from every little pair of pixels in this patch. And you sum them up and make a little histogram of how often each gradient direction occurs in this quadrant of this patch. So we have 4 quadrants, and here 4 gradient histograms. And then we take all these histograms and stack them up in a feature vector. And actually they use, I think, 4x4 rather than 2x2 shown here. But you get then a 128-dimensional number that is, on the one hand, very rich and high-dimensional, and on the other hand, allows for a lot of slop. You know, you can change the precise position of the line, you still get the same gradient histogram. And so it's kind of rich enough to be unique, and yet allows enough slop to allow for viewpoint changes and lighting changes and stuff. These things have absolutely taken over computer vision. almost every, or not every, but maybe a third of the papers just use this and reference this paper. I don't know how many times it's been referenced, but it's one of the big advances in computer vision.
This Jan told me it's the most heavily cited paper of all time.
Okay, well there you go. I'm going to, of all papers?
That's what Jan was calling.
All right, okay, fine. So it's like, it's a big deal, and they're very useful. So what can you do with them? Well, so let me show you. So here's your template. You want to find this object, you want to find that object. Now notice, by the way, they're no longer, wrenches and things. They're kind of more realistic things. And here's your image you want to find them in. So you look for the little, so they're called SIFT, Scale Invariant Feature Transform. You look for your SIFT features, and here's a little box shown around each SIFT feature location. And then you look for all the SIFT features in these guys, and you match them up. So now you've got a computer science problem. You've got, you want to find the most likely position of this thing that explains where you have the most overlap between the SIFT features here and the ones in the image. And so you can find this very heavily occluded frog behind this thing. You can find it because you've got enough of these characteristic features that are lighting up, and you say, well, look, it can only be explained by the frog. We've got 30 out of 300 features in common, and they're all each very distinctive, so it's got to be this frog. And so you can find these little objects. So there's one instance of the train, there's another instance of the train, and it finds them both and finds a frog. Because there's something I haven't told you, which is there's kind of two steps to it. There's finding the location and scale, and then there's finding the descriptor. I told you about the descriptor part. There's a pre-processing step where you find the proper scale and orientation in order to then do this description step. So that's how it's scale invariant.
So each one of these little rectangles is converted into a gradient vector or something.
Yeah, yeah.
So that's how you're matching the tip of the frog over there to this tip.
Yeah, yeah. And you can, and people have just gone to town with these things. Right, so you can, so they're 100 dimensional. You can also vector quantize those things into little, what we're going to call words, or visual words. So you might have maybe 2,000 or 3,000 different bins, and that's your vocabulary of what image elements are. And so now it becomes a computer science problem. You get an image, you find these features, and each one of them is an element in a histogram of possible. So you could look at a training set of images and do so-called vector quantization on them to find these cluster centers of these SIFT descriptors. And
it turns out that if I do this on lots and lots of images, I only get a few thousand.
No, you dial that in, how many you want to get. So it really depends on your tolerance for noise. But I'm just sort of quoting the number that people report is high enough to really distinguish objects and images. So now you look at this image and you get this histogram of how many times you saw each of your 2,000 or 3,000 possible words. And now you go and compare it with your training set of images of cars and say, well, do I have a similar histogram or not a similar histogram to that image of cars? And now it becomes a kind of computer science problem of how much do these two histograms overlap? How much spatial variation do I want to allow? Now it's back in the realm of quantized discrete things. And now it's a kind of combinatorics.
For good metrics.
Yeah, good metric, good match, find good matches quickly. Now it's a computer science problem. And so there are a lot of combinatorial matching problems to be solved when doing object recognition. So here's one image of a panda. Here's it's a little hard to see, but there are these little feature vectors there, and you want to match them up. See, does this one go with that one? And here there's shown in the feature space, and you can decide how tight you want your bins in this feature space to be. You can also have bins in spatial position. So there are a lot of nice computer science problems here. And if you're interested in these sort of combinatorial search problems, this is a great domain for you.
So if you...
Mr. has told me that he thinks that he will be retired before a computer can reliably recognize a kitten.
Huh.
Do you think that's right?
Depends on when he's going to retire.
But if you had an algorithm which did well on combinatorial matching problems, that probably be helpful.
Yeah, yeah, definitely. Yeah. So, and you know, there's this big issue of the distinction between so-called instance recognition and category recognition. If you just want to find this one magazine cover, well, then you can find the exact same ones. But if you want to cover all categories of chairs, then it's a big problem, and it's a combinatorial explosion problem, the kind that computer scientists handle so well. So, anyway.
Well, we probably have people in our lab who can prove to you that it's PPAD complete or something.
Okay. Okay. Yes. And then I just want to advertise Suh's work because I like it so much. This is label transfer. This is another, this kind of third approach to doing object recognition. And this is, I call it brain dead vision. It's very cute and brain dead in the most positive sense. So
We love you. You don't.
no, it is a positive. So here's the story. You have an input image. You want to identify all the objects in it. You have this data set that I haven't told you about yet, but you make it somehow, which has lots and lots of images, all of them labeled with the labelings that you want. And then you rely on the impoverishment of the visual world that there aren't all that many images out there. And if you have some new image, it's got to be like something in your data set, and you've got that thing in your data set labeled. So now all you have to do for this brain dead vision, if you want to call it, is to find a nice correspondence between this input image and this one from your training set, which has labels on it. And so that's what Suh has done. And he developed this method called sift flow, which uses those features I described and comes up with a sort of meaningful correspondence between these, and then lets you drag those labels back to your input image. So here's how it works. You have an input image. Here's a visualization of these sift features, color-coded according to the first three principal components. And then here's this warping. Let's see. Yeah, the warping of this image to the training set images. Here's the corresponding warped sift detector. And then here's the warped annotations. So now here's the game. You have all these warped candidate annotations to describe this image. You want to combine them all, sort of adjudicate between them, come up with a single best labeling. Well, that's pretty easy by this point because they're all registered, and you can have them vote. And here's the output labeling from this image. And all through this system, it really knows, as it were, nothing about images. It's just got this nice label training set and knows how to match up images to each other. And it grabs the label, sucks up the labels from the label training set, and gives you a new labeling. And look how well it does compared with ground truth. And they have these remarkable numbers of like 75% of the pixels are actually accurately labeled, which is just beautiful. And it's a kind of exciting third approach to the object recognition problem.
Second column, the third column?
Let's see. Second column. So I guess what's not shown yet in this photo is the original data set pictures, or maybe they're. Sorry, I go back. I think they're not in this. Yeah. So, anyways, I think I didn't grab them from your slide. But so these are sort of pre-warped. So what you're not being allowed to see in my display of it is what these look like before the registration to this guy. But they were, 3 photos of cars in traffic, but looking significantly different from this. And then the beauty of this SIF matching is to be able to take these in a way I also haven't described and align them properly to these. And then once you've got them aligned, you just grab the labels from your training set and come up with this labeling. So I think this will have a lot of influence. It got this Best Paper Prize at the main computer vision conference, and so I expect it'll have a lot of influence. So I just wanted, in the closing part, I just wanted to show you. So last week I went to this conference, this workshop in Banff, Canada. It was beautiful. And it was on computer vision and the internet. It sort of happened to have really, a very good approximation to just the top people in the field of computer vision there. So I went around and asked them, what can computer science tell computer vision? Because I wanted to help preparing this talk. So here are some of the answers I got. So let's see. From this trio, the modal response was nearest neighbor search in high dimensions. That's really going to help computer vision. And it can be helped with category recognition. Let's see. oh yeah, nearest neighbor search, but taking into account our, sorry, should be our, not our, our particular data, or tell us what questions we should be asking about our data in order to do nearest neighbor search well. That would be helpful to us. And then Rick Solitsky started just free associating. Okay, how do we store all our memories, concepts, objects in a very large database? So again, how do we manage this very large database that we know is going to be helpful to us?
Why only 20 dimensions?
A KD tree is only useful to us in objects of up to 20 dimensions, but we have much higher dimensional objects that we need to work with. A lot of people mentioned parallelism. How can we exploit it? Help us with that. We know that LSH is supposed to work for doing high-dimensional nearest neighbor search, but in practice it doesn't work as well as we want it to. So this is a problem, and there are many references, but here's one reference. Okay, Shayavidan had a nice, really crypto-like computer science. It helps. He's made this little field he calls blind vision. So he envisions a future where, so I have an image and you have an algorithm. I don't want to share my image with you. You don't want to tell me your algorithm. But we want you to process my image with your algorithm. How can you do it in a secure way? So for example, Alice has an input test pattern. Bob has a classifier. And Alice wants to have, the output wants to be the result of this classifier on this image. And Alice just learns that result, but nothing else. And Bob learns nothing about the test pattern X. So you have a secure set of face security images that you don't want to share with anyone, and somebody has a face detector that they don't want to tell you about, and you apply them and get the answer without anybody learning anything they shouldn't know.
Pretty sure cryptographers have solved this in theory. Right, Andrew? Not fully homework, but you can show me.
By the way, where's the help? I thought the nearest neighbor called.
She's getting the kid.
Yeah, I'm not sure, but I think it might be the foundation of life.
Our cryptographer went to pick up her kid.
Oh.
Sure, yeah, I'll know
She was here in the
But I
beginning.
think that's the hard problem that a certain class of interrupted systems are based on.
Huh. Oh, you mean that you're not going to be able to help us with this?
Not this one. Now she's referring to a different problem.
Nearest neighbor.
Yeah, I see.
Except the people do it pretty well.
Yeah.
Okay.
But he has more. He knows more.
Yes, he's on.
That's true.
This is not like
So
some worst
that's not
case.
encouraging, but it's not
Okay.
disastrous.
These are very specifics.
Okay. So this blind vision is really it's not really a subfield. It's more just one paper that this guy published, but you might find it interesting. There might be like it's interesting if we have distributed processing on a given image. So another thing, you might have a data. So I might have an image that I want to have some hole filled in, and you have a big data set of images, and you're just great at filling in holes, but you don't want to show that to me, and I don't want to show you my image, but we want to find out whether there's a good match of this image to your data set.
CIA talking to KGB.
Yeah. Okay. Yeah. I see.
In theory.
Okay. Okay. Deva Ramanan said he wants a way to easily evaluate some function over a power set of all segmentations. Oftentimes, if somehow we magically knew what the right segmentation was for an image, everything would be easy. You could just take the little segment, check it into your object recognizer, and be really quick to find everything out. If only we knew the right segmentation. Well, if somehow we could magically try out all possible segmentations and evaluate each one of them, that would be great. So that's sort of a pipe dream. I don't know if that's possible, or if you can just prove for us that it's not possible. So anyway, that's another problem. Evaluate some segmentation-dependent function over all possible segmentations. And that would have lots of applications. Alyosha Efros, a funny guy. Well, he just said the needle in the haystack problem is what we really need to solve. Find the signal or clusters when there's a lot of noise. Find the pattern, ignore the noise. So him and me and two others had these crazy hats on. He said, find the picture of, from pictures of the four of us with hats on, determine that it's a hat that we have in common. David Lowe, the guy who invented those features, what does he think needs to be helped? He thinks we need better features. So an artist can draw the end of an elephant's trunk, and you know immediately what it is. You know, it just absolutely captures the whole thing. So how can we capture the essence of these visual objects with the local features? And then just one last thing. If you really want to publish, I want to tell you what the culture is. For a long time, people published if-only papers. Like, if I only had a segmentation, here's what I would do. And, well, we no longer can publish those papers. You really have to do end-to-end systems now, because who knows if you can get that segmentation. So it's really much more empirical now than it used to be. There's, in practice, I think, a lot of overhead in coming up to speed on the filters and representations you need for images. You need to validate your algorithm on a data set, or it can't get published. There are these competitive conferences that have about 20 or 25% acceptance rates. So that's kind of a pain. There's always a little random coin toss whenever you submit something. On the other hand, if you don't publish there, nobody knows about your work. So there are these 4 conferences. You got to get it into one of those, or else no one learns about it. Well, yeah. I mean that's yeah. Yeah. Yeah.
Has there been an example where people wrote an if-only paper and then the if was actually shown possible and it just didn't work?
The bacon and eggs problem.
Yeah. I'll think about that. I can't think of one offhand. But I mean, for example, there used to be a lot of work done. If we just had a perfect segmentation of all the edges, here's what we could do. But then you just can't get that perfect segmentation.
And I assume those if-only papers are validated by, for example, doing the segmentation manually. So it's not totally.
Yeah, but you know, you've got this high-level processor in there doing that manual thing. Yeah. Okay. Okay. Right.
They're not just making it up.
Right. But so it's best to. So the story of this slide is that it's best to collaborate to maximize your chances of getting in. And if you want to collaborate, here's a lot of people at MIT who would be, love to work with bright theorists from Microsoft. I mean, I can't guarantee that they'll all work with you, but I can guarantee they'll all take you seriously if you send them an email saying, I'm interested in doing this.
The deal here is the theorists at MIT don't want to work with these people.
I guess, yeah. No. But anyway, this is a list of, the list of the people doing vision and computational photography work at MIT. And there's a lot of us, and it's a very exciting place to be. And what else? Oh yeah, so I just want to have some eye candy at the very end. So here's one. This is not vision. This is work I've had really a lot of trouble getting published. We finally got it published, but it's a lot of trouble. And because there's no good reason for it, that's why it's hard to get published. We've made a system where you give us a photograph and we combine it with a large database of images, and we just start driving from your photograph. We, in effect, give you kind of a joystick. You can go forward, you can go left, you can go right, you can go back, starting from this photo. And we go and find photos that would fit well with the left half of this picture and blend it in well, and we make a little video. So here, this is the input picture. Now let's start driving. So here's a video, kind of turning left and right from this input image, and all of this is made up from a large collection of Flickr photographs. And yeah.
Photographs of the same scene, or just photographs?
No, just photographs. Yeah. Yes. Yes. Yeah. Yeah. So. Oh well, I'm going to show you other ones. If that's okay. So here's an original. So we represent it as, again, kind of similar idea: orientation gradient, histograms of orientation gradients, a little bit of color. That's our representation. We find that to get this to work, we couldn't just grab all Flickr images. We had to grab them and then filter them into little themes. Otherwise, we'd jump crazily from one theme to another. So we developed a theme classifier that would classify Flickr photographs as skyline or landscapes or streets and others. And then we got this collection of several thousand, about 100 or 200,000 within one theme. And then we have forward motion, rotation, camera pan. And then this is kind of the obvious thing. So here's your input. You want to find out what would be there. So you translate and say, well, now I'm looking for an image that has this over on this side, and then I don't care what it has over on that side. And you look for a good match, and then you kind of wiggle it around. Then there are these graphics techniques that we used to find the best match. We wiggled it around till they overlapped the best, and then we found the best seam between the two images, broke there. We used the so-called Poisson image editing, which finds the least squares reconstruction that respects all the gradients, except it ignores all gradients along this seam. So it lets you minimize the reconstruction artifacts. So there's the blended between this one and the one we found there, and it looks pretty seamless. And you can do the same thing rotation. For rotation, now we want to find a picture that looks like this on the left side, and you can simulate the whole thing. And so here are some composites that we made, which are all just made up. And let's see. Oh yeah, okay, so here, let me show you some of the ones. So let's start from a famous place and just go off to the right, see what's there. So here's, we start from the Hollywood sign, and let's go off to the right. So,
you can find terrorists this way. You can go to the CIA, tell them you can find terrorists.
right. So in our quest to get this published, we kind of brainstorm applications. So one possible one is this gives you an infinitely large photorealistic virtual world. So maybe for games, for Second Life or whatever, you could use this as a way. Oh, here's another one. Let's see. So we go in. We find an elephant. We back up. It's from their Indian phase.
How much overlap is there between the techniques you're using and what Photosynth does?
Well, the feature matching is going to be similar, both based on...
Photosynth relies on geographical information, right?
Yeah, it does it the right... It's honest about it. And we blend a little more heavily than they do, I think. And now here, I know you've all wondered what is off to the right of the XP screensaver. So there it is. So that's it. Thank you very much. Okay. So you've all sort of asking questions the whole time. I'm happy to answer questions, but it's also the end of the time, so we can stop there.
So bull is off to the right.
It's too late to get this into Windows 7.
Yeah.
Yeah, just randomly generate. Yes, it's a screensaver. That's what it is.
Yeah.
It's a screensaver.
Yeah. So anyway.
It'd be an amazing screensaver. But you wouldn't get any work done. You'd just be watching it all the time.
Start a picture with your daughter.
Yeah. So anyway. Well, thanks a lot.